Hydrogen is the simplest, the most abundant element in the universe. The story of hydrogen begins in the stars. It was the first element to form after the Big Bang around 13.8 billion years ago. This primordial element has played a crucial role in the evolution of the universe. The name hydrogen comes from the Greek words hydro and genes, meaning water forming. This name was given by the French chemist Anthony Lavoisier in 1783 after he discovered that hydrogen gas when burned produces water. However, the journey of discovery of hydrogen started earlier. In the 16th century, the Swiss alchemist Paracelsus observed that a flammable gas was released when metal reacted with acid. This gas was later identified as hydrogen by the British scientist Henry Cavendish in 1766. His meticulous experiments revealed that hydrogen was a distinct element and he described its properties in detail. Hydrogen is the first element on the periodic table with the atomic number 1. It has a single proton in its nucleus and 1 electron orbiting around. This simplicity makes hydrogen unique and fundamental to the study of chemistry and physics. In its most common form, hydrogen exists as a diatomic molecule, meaning 2 hydrogen atoms bonded together. It is a colorless, odorless, and highly flammable gas at room temperature. Hydrogen is incredibly abundant, making it about 75% of the elemental mass in the universe. It is found in stars, including our Sun, where it undergoes nuclear fusion to produce helium and release vast amount of energy. On Earth, hydrogen is present in water, hydrocarbons, and all organic matter. Being light and having high energy content, hydrogen is a promising candidate for clean energy solutions. It is used in fuel cells to generate electricity with water as the only byproduct, making it an environmentally friendly alternative to fossil fuels. Hydrogen holds a special place in the periodic table. It is located at the very top in Group 1, Period 1. This position is significant for several reasons. Firstly, being in Group 1, hydrogen is often associated with the alkali metals, which include elements like lithium, sodium, and potassium. However, hydrogen is not a metal. It is a non-metal. This unique placement highlights in its dual nature and versatility. Secondly, hydrogen's position in period 1 indicates that it has only 1 electron shell. This shell contains a single electron, making hydrogen the simplest and the lightest element in the periodic table. Its atomic number is 1, reflecting the presence of just 1 proton in its nucleus. The unique characteristics of hydrogen stem from its simplicity and its ability to form bonds with a wide variety of elements. Hydrogen is the lightest element with an atomic mass of approximately 1 atomic mass unit. This lightness makes it highly mobile and reactive, allowing it to participate in a vast array of chemical reactions. Hydrogen can form both ionic and covalent bonds. In ionic bonds, it can lose its single electron to form a positively charged ion. In covalent bonds, it can share its electron with other atoms, forming molecules like water and methane. Hydrogen has 3 naturally occurring isotopes: protium, deuterium, and tritium. Protium, with no neutrons, is the most abundant. Deuterium, with 1 neutron, is used in heavy water for nuclear reactors. Tritium, with 2 neutrons, is radioactive and used in fusion research. Hydrogen is highly reactive, especially at a high temperature. It readily combines with oxygen to form water, releasing a significant amount of energy in the process. This reactivity makes hydrogen a potential candidate for clean energy sources such as fuel cells. Hydrogen is the most abundant element in the universe, making up about 75% of its elemental mass. It is the primary fuel for stars, including our Sun, where it undergoes nuclear fusion to produce helium and release energy. Hydrogen exists in several forms, each with unique properties and applications. Molecular hydrogen is the most common form of hydrogen, consisting of 2 hydrogen atoms bonded together. It is a colorless, odorless, and highly flammable gas. It is used in various industrial processes, including the production of ammonia and the hydrogenation of fats and oils. Atomic hydrogen exists as individual atoms. Atomic hydrogen is highly reactive and rarely found in nature. It is used in certain industrial applications such as atomic hydrogen welding, where its high reactivity is beneficial. Hydrogen can also exist in ionic forms. A hydrogen ion with a positive charge is essentially a bad proton. Protons play a crucial role in acid-base chemistry and they are involved in many biochemical processes. A hydrogen ion with a negative charge is hydride ion. Hydrides are found in various chemical compounds and they are used in some industrial process. Each isotope of hydrogen has distinct properties and applications. Protium is lightest and most abundant isotope with no neutrons. It is essential for forming water and organic compounds. It is also used in various industrial processes such as the production of ammonia and methanol. Deuterium is used in heavy water for nuclear reactors as a neutron moderator. Deuterium is also used in scientific research, including studies of reaction mechanisms and tracing elements. Tritium is a radioactive isotope with a half-life of about 12.3 years. It emits low-energy beta particles. It is used in self-luminous paints for watches and exit signs, as well as in fusion research. Tritium is also used as a tracer in environmental studies and biological research. There are several methods to prepare hydrogen gas in the laboratory. Two common methods are the reaction of acids with metals and the electrolysis of water. The method of reaction of acids with metals involves reacting a dilute acid such as hydrochloric acid with a reactive metal like zinc. In this reaction, zinc reacts with hydrochloric acid to produce zinc chloride and hydrogen gas. Electrolysis involves passing an electric current through water to decompose it into hydrogen and oxygen gases. In this process, water is split into hydrogen gas and oxygen gas at the electrodes. Steam reforming is the most widely used method for producing hydrogen. It involves reacting natural gas, primarily methane, with steam at high temperature to produce hydrogen, carbon monoxide, and a small amount of carbon dioxide. This process is highly efficient and cost-effective, making it the preferred method for large-scale hydrogen production. The efficiency of hydrogen production methods varies depending on the process itself. Steam reforming method is highly efficient with an efficiency of around 65 to 75%. It is the most cost-effective method for large-scale production but produces carbon dioxide as a byproduct. The efficiency of electrolysis ranges from 60 to 80% depending on the technology and energy source used. While it is less efficient than steam reforming, it is more sustainable, especially when powered by renewable energy. Syngas, short for synthetic gas, is a mixture of hydrogen, carbon monoxide, and often carbon dioxide. It is a versatile intermediate used in the production of various chemicals and fuels. Syngas is not a naturally occurring gas, but it is manufactured through various industrial processes. The primary components of syngas, hydrogen and carbon monoxide, make it a valuable feedstock for producing synthetic natural gas, methanol, ammonia, and other chemicals. Additionally, syngas can be used as a fuel for power generation and as a reducing agent in metallurgical process. There are several methods to produce syngas, each involving the conversion of carbon-containing materials into a gas mixture. The most common production methods include steam reforming, partial oxidation, and gasification. Steam reforming is the most widely used method for producing syngas. It involves reacting natural gas, primarily methane, with steam at high temperature to produce hydrogen and carbon monoxide. This process is highly efficient and is commonly used in the chemical industry. Partial oxidation involves reacting hydrocarbons with a limited supply of oxygen to produce syngas. This method is faster than steam reforming but less efficient. Partial oxidation is often used when steam reforming is not feasible. Gasification involves converting carbonaceous materials such as coal, biomass, or waste into syngas by reacting them with a controlled amount of oxygen and steam at high temperature. Gasification is a flexible method that can utilize various feedstocks, making it an attractive option for syngas production. Hydrogen is a colorless, odorless, and tasteless gas at room temperature. It is the lightest and simplest element, consisting of just one proton and one electron. Hydrogen has an extremely low density of about 0.08988 grams per liter at standard temperature and pressure. This makes it much lighter than air. Hydrogen also has a very low boiling point of minus 252.87 degrees Celsius, which means it remains a gas under most conditions on Earth. The melting point of hydrogen is minus 259.16 degrees Celsius. At this temperature, hydrogen transitions from a solid to a liquid state. Hydrogen is slightly soluble in water and is more soluble in organic solvents. Its solubility in water is about 1.6 milligram per liter at 20 degrees Celsius. Hydrogen has high thermal conductivity, which means it can transfer heat efficiently. This property makes it useful in applications where heat dissipation is important. Hydrogen is highly flammable and can form explosive mixtures with air. It burns with a pale blue, almost invisible flame, producing water as the only combustion byproduct. Hydrogen is a highly reactive element, especially at a high temperature. It readily combines with other elements and compounds, making it a key player in many chemical reactions. Hydrogen reacts explosively with oxygen to form water, releasing a significant amount of energy. This reaction is the basis for hydrogen's use as a clean fuel. Hydrogen reacts with halogens, such as chlorine, to form hydrogen halides. For example, hydrogen reacts with chlorine to produce hydrochloric acid. Hydrogen chloride is a common product of this reaction. Hydrogen forms a variety of compounds through different types of bonding. Hydrogen commonly forms covalent bonds by sharing its single electron with other atoms. This type of bonding is seen in molecules like water and methane. Hydrogen can also form ionic bonds, particularly in the form of hydrides. For example, in sodium hydride, hydrogen exists as a negatively charged ion. Hydrogen bonding is a special type of dipole-dipole interaction that occurs when hydrogen is bonded to highly electronegative atoms like oxygen, nitrogen, or fluorine. This type of bonding is crucial in biological molecules like DNA and proteins. Hydrogen plays a significant role in acid-base chemistry. In acids, hydrogen is present as a proton. For example, hydrochloric acid dissociates in water to release hydrogen-positive ions. In bases, hydrogen can be part of the hydroxide ion. For example, sodium hydroxide dissociates in water to release hydroxide ions. Hydrogen can exhibit amphoteric behavior, meaning it can act as both an acid and a base. Water is a classic example, as it can donate a proton to form OH- or accept a proton to form H3O+. Hydrogen is widely used in various industrial processes due to its unique properties. One of the primary uses of hydrogen is in the production of ammonia through Haber-Bosch process. Ammonia is a key ingredient in fertilizers, which are essential for modern agriculture. Hydrogen is used to hydrogenate fats and oils, converting unsaturated fats into saturated fats. This process is crucial in the food industry for producing margarine and other hydrogenated products. Hydrogen is used in hydrocracking and desulfurization process to refine crude oil into gasoline, diesel, and other valuable products to remove impurities and improve the quality of fuels. Hydrogen is gaining attention as a clean and sustainable energy source. Hydrogen fuel cells generate electricity through a chemical reaction between hydrogen and oxygen, producing water as the only byproduct. This technology is used in various applications like electric vehicles, backup power systems, and portable power devices. Hydrogen is used as a fuel for vehicles, offering a clean alternative to fossil fuels. Hydrogen-powered vehicles emit only water vapor, making them environmentally friendly. Hydrogen plays a crucial role in various scientific research areas. Liquid hydrogen is used as a coolant in cryogenics due to its extremely low boiling point. It is essential for cooling superconducting magnets in applications like MRI machines and particle accelerators. Hydrogen isotopes such as deuterium and tritium are used in nuclear fusion research. Hydrogen is used as a reducing agent in various chemical reactions and synthesis process in the production of important chemicals and materials used in pharmaceuticals, plastics, and other industrial applications. This was just a brief introduction to hydrogen. There is plenty to know more. Keep learning, and thanks for joining me.